We learned that motion has many types. They can be visualized using graphs that depict changes in quantities related to the movement. One such graph is a distance-time graph. The distance-time graph visualizes the distance traveled, d, by an object over time, t, which are represented by the vertical and horizontal axis respectively. To illustrate linear motion, let's consider the example of a car moving at a constant speed. Imagine you and your child are on a trip, but your child won't stop crying due to hunger. As the car is about to pass the police patrol, you maintain a humble speed of just 4 meters per second. How do you picture the car movement on the graph? Remember that constant speed means you cover the same distance per unit time, in this case per second. Here, the distance you reach each second is 4 meters. If we choose the police patrol as the reference point, where the distance, d, is 0, then after 1 second, the car has moved 4 meters away from the police. The next second car is 8 meters from the police patrol, and so on. In the graph, this data is shown as small dots at the intersection of the distance and time axes. As you see, the graph slopes up, indicating the increase of distance. The slope or gradient of the graph implies the value of speed. Why? It's because the rise over the run of the slope represents distance over time, which is equal to the speed formula. A steeper slope indicates a higher speed because more distance is covered per unit time. Conversely, a shallow gradient indicates a slower speed. Since the upward slope shows that you move forward, now you can tell what a downward sloping line indicates. The decreasing distance over time means you're moving backward, approaching the point of reference. However, it is still a straight line, so the speed remains constant for that time interval, despite being negative due to the change of direction. So does it mean that speeds can change over time? Absolutely! In fact, it happens all the time in real life. A moving object that changes speed experiences either an acceleration or deceleration. For instance, if you accelerate at a constant rate of 2 meters per second squared, then its speed increases by 2 meters per second every second during acceleration. This makes the distance rise exponentially, hence form a curve. The similar graph also appears when you're plotting a free-falling object, whose motion is affected by gravitational acceleration, g, of 9.8 meters per second squared. The speed is 9.8 meters per second squared faster than before every second, making the curve steeper. Since the speed is always changing, we're only able to calculate instantaneous speed. Now, how to visualize the car motion when you stop the car. The car is not moving at all, so the graph is depicted as a horizontal line for a whole second. Now, look at this graph. Can you tell the object speed of every section? Share your answers in the comments below. Say from 20 years of taking shortcuts through the living room, instead of obediently walking down the hall and then turning left, passing and trading hateful eyes with the family cat stationed there before you finally arrived at the kitchen. By using a bit of theory and simple multiplication, you could actually estimate the numbers and continue with your life. But to do this confidently, you need to first understand squares and square roots. Here you'll be introduced to these lovable concepts of squares and square roots. Let's jump into it and get started. First of all, what do we mean by the square of a number? In mathematics, square can possibly mean two things, a type of geometry and a product of self-multiplication. When a number is multiplied by itself, the product is known as the square of that number. For example, if we multiply the number 2 by itself, that is 2 by 2, we will get 4. Now 4 will be called the square of 2. It is written as 2 squared equals 4, which means the same as 2 times 2 equals 4. Similarly, if we multiply 4 by itself, that is 4 by 4, the product will be 16. This can also be written as 4 squared equals 16. We can say then that 16 is a square of 4. Meanwhile, square roots are the inverse operation of squaring. So, the number that is multiplied by itself is called the square root. A square root is represented by the symbol radical sign. In our previous example, 2 squared equals 4. Hence we can say that 2 is the square root of 4, or the square root of 4 is 2. Conversely, 4 is the square root of 16. Therefore, the square root of 16 equals 4. 4 expresses that the square root of 16 is 4. Back to the shortcut. You know that the hallway is 6 meters long, while the distance from the turn to the kitchen is 8 meters. Can you tell what the square of 6 and 8 is? Exactly. The squares of 6 and 8 consecutively are 36 and 64. Thus, the shortcut distance to the kitchen is equal to the square root of the sum of 36 and 64. This yields 10 meters, which is 4 meters shorter than the usual route you walk on every day. Imagine the time and energy that you would have saved until now.
Mathematics. A great philosopher, Galileo, once said, "The laws of nature are written in the language of mathematics." Math is a human language just like English because it allows people to communicate with each other. Even in the ancient times, people needed it to conduct trade, build pyramids, measure long distances. It is the powerful aid to the human mind and the most glorious creation of the human intellect. Math is everywhere, from the shapes of planets to the properties of an atom. Our universe is completely mathematical. It is your identity. You can't quote your age without it. It is the historical timeline. Math is used by engineers to build infrastructure and telecommunications, by doctors to prescribe the right dose of medicine, by researchers to prove a research, by pilots to navigate, by politicians to count vote, and even by gamblers to find their chances of winning, and this list goes on and on. Maths disciplines us. Even time is a measured quantity. We couldn't have known the exact time if we didn't know numbers. It is the very foundation of the modern civilization and is the key to problem solving, logical reasoning, and creative thinking. Hence, the very act of learning math helps us acquire accurate thinking, which is necessary in all the pursuits of life. We all need maths, but one might think, why are so many kids confused by it? Is it because only a few of them are determined for maths, while others are not? This isn't the case at all. It's just a myth that there exists a thing known as a math brain. The idea is disproven by the brain science. It's because somewhere along the line, we've taken this language of math, which is about the real world, and abstracted it beyond recognition. And that's why most of the kids are confused. It's high time that we change this approach, and there you are. Math becomes intuitive and easy to understand. Mathematical thinking not only builds young minds, but all kids need it to imagine and build a future that doesn't yet exist. Understanding has no end to its depth, and mathematics seeks the highest standards of understanding, so it will definitely take you to the next level. The next time you find yourself frustrated in a math class, maybe think about where maths could take you.
Wow.